All right, so welcome back to the second part of our Cloud Computing and Big Data lecture 5 today about MapReduce. And it's really a computing paradigm that we learned in the, let's say, first part of the lecture for different reasons, mostly because you see that dividing and then conquering problems, the idea how to handle those problems in itself was already rooted in computer science computing paradigms and is very old. And of course, some aspects are added to it that we had in the first part, like, logical programming, Lisp, these languages influenced a little bit Google, and lots of other ingredients which were more from the practical side, saying that we have lots of errors, we have suddenly lots of more data, and all of top of this is that the machines that handled data at that time were actually getting more and more complex. And with this also, we need to have something which hides the complexity. So this is what we can take away from the first part, that MapReduce is really aiming to solving these aspects and being, let's say, maybe also a kind of cheaper solutions, because at that time also the big data center money for this, for the large systems, especially the interconnects of high performance computing systems and large installations, are very expensive. So the idea was creating a software for certain part of problems. We're not solving everything, right, with MapReduce. So we will see in this lecture at the end that there are limits to MapReduce, and no one is saying that MapReduce is now the modus operandi, so to speak, for everything. So it has its advantages, and we will discover those in this part of the lecture. And also at the end of the lecture, while we had some application examples, also look on the limits of MapReduce, where you would think that they're actually using MapReduce perhaps doesn't make sense, or you have some interesting and smart additions to it. So let's go to the second part of the lecture. And for this, I would just like to connect again to something we a little bit put out of the horizon. As I said earlier, we changed a little bit the slides and the lecture setup based on student feedback, which meant like we put more practical aspects directly in front, using Apache, products, Spark really in practice already in the second and third lecture to really get on with the assignment 1 early. Of course, what we left out with this was a little bit a fundament, a really basement where Hadoop and Spark and other solutions in the, let's say, MapReduce ecosystem really build on. And this is a reliable file system. And this is by far now the major implementation called Hadoop distributed file system. But you see already in the original paper from Google, they had the same aspects in mind. Of course, nobody at that time could see that Hadoop would be so massively successful as it is today. Of course, this was a movement. And then again, think about that an organization does not need to do everything with Hadoop. So some things can be done with Hadoop, some other parts maybe with Spark, or for, let's say, completely different tasks, you go even to a HPC machine, you will see. And basically, this is a very important part. But the hardware aspect of this errors, of course, is something to consider. And with this, we need this file system that somehow deals with it in one way or another. And so this will be then now shedding a little bit light on what we left out in the couple of lectures before, while indirectly using it, so to speak. But it also shows you a good example that you could use it without knowing anything about it. So of course, if you go back to our slides before, that is exactly what the goal was of these data frameworks. That's, for instance, not really possible so easily with high performance computing. You have a parallel file system, you have parallel file formats where you write in, so they have to do much more considerations of the files, the file structure, the data structures. So this is an interesting aspect. Of course, here you have the key value pairs, which we had in a couple of very simple examples with a word count, I think, let's say, materializing quickly. But depending on how you formulate this key value stores, and then the key value data coming out of it, you fuel maybe into Spark, or basically in Hadoop is MapReduce. You basically then have also the very complex solutions, and I will show some in practical lecture 5.1. Here, for the sake of learning, of course, in this lecture now we keep it simple to really understand the basic concepts, and the same is true for the Hadoop distributed file system. So again, just a reminder for revisiting this, we said we have lots of different problems. Basically, hardware failures, one node or 1% of the node, so to speak, is always common of having some error. Hence, it will be never 100% utilized because it's simply not possible from the hardware even. But we have to deal with it. And even if it's CPU, network, software failures, there needs to be different considerations on it. So some of it is maybe data is away. So one of the nodes is simply down that maybe has precious data on. So what to do then if you want to do machine learning and learning from data, but your data is not accessible? Well, then you don't do machine learning. So it's of course something to think about. So our framework or the data processing machinery with MapReduce and the file system underneath should be handling this. What about if a task is, working for an hour, creating a beautiful model, maybe in machine learning terms of speaking, and suddenly it crashes? The model is gone. So do I want to resubmit this manually? Do I want to see where exactly was the problem? No, I want a framework that maybe resubmit parts of it automatically if there was an error. If there was a hardware error, maybe there was also a different error, you don't know. Could be a bug, actually. What we have in Jülich every now and then, to be honest, right, is that also vendors, they do bugs in big systems that you rely on. So if you rely on this as a data center, then of course, you just have to live with it, and the vendors usually come very quickly to fix those bugs. But it happened in the past, and also if you think about the size of these installations means that sometimes this software, the schedulers and so on, have never operated in such a big environment because these systems are such unique. Of course, now we see really more and more data centers in the last decade, but when you go back where MapReduce was created in 2004, where this all have begun, so to speak, to creating larger and larger data centers, this was, of course, a completely different technology than we see today. It really matured a lot. That's what I'm saying, the last 15 years. But still, we didn't rule out completely all the errors. So there's still work to be done. And of course, then we have different aspects of now requirements really to this parallel file system and the MapReduce engine in the framework of Hadoop to really deal with this. So what it means for, kind of data center then is to get customers, for instance, is to be a good data center, right? So I think that's what everybody would say. But also in this light, it's really important to understand what really means to be a good data center. You of course have this now with relevant statistics. You see how quickly people get in the support queues answers on this level, but also on the level of faults and errors and failures. Of course, this is all measured usually. And here is an interesting terminology, so to speak, that I would like to clarify. Basically, this formula often also actually is appearing in exams. So maybe it's good to have a little bit on attention now. Where you have a sort of term which means a mean time to failure, and there you have basically then the mean time to repair, right? So these are two important terminologies that you have there, and from this you have a little bit this so-called mean time between failures, which is of course a bit easy to compute then if you have both there, right? The time to failure and then the time to repair, you just add this on. And then basically you can actually go with between failures. But more interesting for us is how about the node availability or software module availability, whatever it is, what system you have. There's a rule that basically you have this module availability that you see here. And it's basically valid for non-redundant systems, right? Which you then repair. Now, what we will add was replicas, and redundancy has a little bit of different value, but this is just clarifying for you that these metrics really exist also in a real practice. And you cannot go to customers, and some of them that pay you a hell of a lot of money for these, to have really dependability of your cloud data center that you basically rent resources from. What it reflects now is actually two things. How reliable is it in practice, right, to use services, how reliable it is to use my Apache Spark cluster, and then have a different results. Is it crashing all the time? And then the availability. So is it always down for maintenance, or can I use it when I want in the company? Because my employees doesn't want to wait for many hours if I pay a lot of money. So these are kind of two related aspects which then really quantify this dependability that you have on clouds. And it drives a lot of money in the clouds. You will also see that if you want to explore a little bit, go into some of the cloud providers we have discussed, MS Azure, but also Amazon. We will talk about this in subsequent lectures. Also, where you then see the more premium resources you buy, the more expensive it gets, right? And of course, there are different contracts that you can rent, so to speak, in this cloud. And with this, getting a higher dependability, of course, costs you also money. Now, this was really a more theoretical view on this, and I think it's clear that these data centers are a high cost, so they have to justify the costs. They have to see, and also making customers happy in the end, right? So with this, even if you have hardware faults on all levels, you have operational faults, which, by the way, is often the most primary cause of failures in these systems today, right? Because there's a wrong installation, it directly affects a lot of nodes. While a hardware, maybe a chip gets too hot, then the whole rack has maybe a problem. Not even this, you would say the board, which has a different CPUs in it, or something like this can be exchanged. But when someone has a software problem, usually the problem is larger. For instance, a parallel file system that is operated often, these installations have a problem, then it affects many nodes. Of course, there are also different approaches. I don't say that MapReduce is now used to solve all the data center problems in this, right? That should be a very important aspect here to let you know. There's a complete, let's say, complementary aspect of how you deal with data called the so-called RAID levels, the redundant area of independent disk, with different levels, which means you keep maybe complete redundancy of data in different RAID levels, or you have a systematic block entity. That would be going too far in this particular course, but I encourage you to look also into this if you want. It's a very interesting aspect also to be prepared against, let's say, several faults that you have in a data center. However, the RAID levels, of course, directly are more related to storage for data. Now, with MapReduce, we have two things, or essentially to be more precise with Hadoop, we have two things. We have a MapReduce engine for computing, but we have also the specialized file system. And the specialized file system is different from the RAID levels. It takes ideas from the RAID levels on, replicas, we will talk about it, but still it's, let's say, a very specialized file system that kind of assumes that there will be always errors. And this was a kind of design idea that drove the design of HDFS, which now fuels lots of our big data ecosystems in clouds everywhere. So what does it mean to have a specialized file system? So basically you would see that it has still the idea of running with typical commodity hardware. So the file system should be not depending on, like it is in the parallel file system world, on parallel, file formats, on really specific file formats. Here we still think about file and data replication concept, but it can be basically put alongside commodity hardware, and it has very similarity with a distributed file system. In a way, you would say it is a distributed file system even, but it adds a couple of advantages to it. It's not just distributed, it has a bit more power with a so-called inherent data replication concept we will talk about. The also different aspect for is looking at from a distributed file system perspective is that already directly assumes to be faulty, which is interesting. So it will have mechanisms in place to let the MapReduce engine know that I here have a problem, please submit somewhere else, and sorts of things. So when you do this normally, you don't have directly such good feedback on this. And of course, which is also here important, it has a strategy with blocks and basically parts in splitting input files, which are extremely large usually. And with this, you have a kind of parallel approach for them, including a replica strategy. You see this a little bit on the right-hand side. When you, for instance, have the map reduce phase, and you have a couple of workers, of course, you split your input files. You want to parallelize. So this is inherent in the design already. You distribute the data with the replicas and splitting the data. So this is, of course, something which is also not really normal distributed file system. Also, a little bit is interesting that, and you heard a little bit about operating systems, for instance, in these lectures, you probably talked about Unix and POSIX requirements for files. So HDFS is relaxing some of those. So in a way, you are in the Java space with HDFS. So you're not really on the operating system itself, which is actually one of the critics I have to be saying, because when you put this to the Java space, you can already assume it's getting slower. It would be directly on the operating system. Still, it has lots of benefits, not only the replica strategy in itself, but really a system, so to speak, that is optimized for high throughput access to the application data. So in a way, the distributed file systems and parallel file systems, they're very compute oriented. They assume a very homogeneous situation, or if you connect them in the distributed file system work, still operating similarly and, you know, things like that. But with the Hadoop and the HDFS, you have a really, let's say, heterogeneous approach, because with relaxing some of the POSIX requirements, in the end, you don't care. You are in Java space and have lots of possibilities to deal with a file, like breaking it down or handling stream data and so forth. Of course, needless to say, this was, of course, before also an interesting aspect from Google. Before then, it was considered as the Apache Nudge web search engine project. And yeah, so that's interesting history, how that now comes and basically into play years after years of experience with distributed file systems, with parallel file systems in the last installation. And again, what you see here on the right-hand side, which we will also, of course, discuss more in deep now, is the different strategies. You have a master worker paradigm. We will come to this in a moment. We see there's something happening in the data. So there's intermediate files, what to work with this. So this was, if you remember, with the word counts, maybe now the arrays that you sort according to the words, right, that we have seen. So that basically you have the same words all in one nice array, and the reduce task is very simple. So this is an interesting approach of having a whole framework for computing data-centric. And this is, of course, an important part. When you think about, we discussed that data is increasing significantly. The transfer of data is more and more getting harder, especially since 2004 when this was developed. You see all the silos are growing in size significantly. So then you rather basically transfer the compute jobs, what is essentially standing here on the right-hand side, with smaller map jobs at very close to the data. So in a way, what you do with this is creating a so-called data locality scheduling, and you know, the communication in MapReduce, which by the way should be, of course, use less network, use less communication. But this means, of course, in terms of really big data transfers, right? Starting with a large FTP, then waiting several hours and so on. This is not feasible. The other way around is feasible in this approach, where you say you define a smaller task, which means a computing entity, which is not a big HPC machine close to the data, can handle it. Maybe just a smaller cluster, right? Or a couple of so-called pizza boxes, as we will say every now and then in previous times, right? Smaller commodity clusters put together, or systems. But they can handle a relatively easy map task, which was in our example, let's say now the idea of just having basically an index, you know, +1, +1, +1 for the occurrence of different words. That's not computational expensive and can be done by lots of different workers. Of course, it depends on the size of data now, but this is what you do with the splits you see on the right left-hand side. So you see that essentially you would have a big problem on the data, but the data is already there. That should be there showing with the green part, right? The data replicas are already there. You just split, so to speak, the work that is on it working on different parts of this replicas, and we come to the replicas on a different slide, just to understand that this is of course now how to deal with big data and why you have a nicely parallel approach. You can nicely do the splits, because these splits should be very independent from each other. If they would be extremely depending on each other, that in each of the computing count on the index in, you need to know the other split, then it wouldn't work. That would be the example of weather forecast. If the splits, what you see there on the left-hand side, would be an area of the ocean that we discussed with waves propagating over split 4 to split 3, split 2, split 1, and the next waves, they are highly interconnected. That's what we do in the HPC world. Here, this approach would be not really feasible or not quick enough, maybe, if you want, right, to do a proper physical law evaluation and, kind of conclusion or convergence. Hence, you break it up. And we know that it's a divide and conquer strategy of breaking this big, large files that we have and see more and more growing, basically all the data that we have in general in the silos into smaller problems. Then you assign this map task, and you see there already, there are different roles here. There's a master that kind of keeps track what's happening overall, but doesn't do anything. It's almost like a manager. And then you have a worker, right? Which says, okay, here we have lots of work, and the master has a very good overview. That is his work, keeping the overview, keeping to know where is which data. This is very important. And then it could, assign different map tasks to these workers, and they just do this. They don't care about anything, not the global picture. I don't care for what the word counting will be in the end, right? The worker just does this very simple job close to the data. Once you have done this, of course, you have some intermediate file results. So in a way, you have to write locally. And this is another part of the framework, right? Normally now you would say, okay, no, I have my results, which are unfortunately partitioned. So they're kind of on different servers. Now I have to do my own FTPs to bring all the data to one central entity to, then do some summarization. And all of this is now the fancy third that I injected there for the understanding. This intermediate files and the work on it and all the transfer is done by the framework, right? So the sorting, the shuffling, getting the data in a let's say, even if it's local, then to a sort of data structure where then the reduced task can work on, right? So basically have all the communication abstracted away from the user, that only in the user program at the top has to think a little bit of the key and key value structure that we discussed. Then this is already lots of automatism in the process. And the interesting data locality is in part, but also if you see, for instance, that some of them will fail, the MapReduce engine is so smart enough to realize this, since the master keeps track of everything, and then basically could resubmit a job on behalf of this, let's say, worker that is just dead, right? He is basically not pinging back. There's a hardware error, so the worker doesn't work anymore on the data. So let's resubmit it. Immediately to you comes now the question, I hope, now when I do this with data locality and this worker was down at this data where he should work on, then I have data loss. So how in the world should I continue and resubmit now when I don't have the data, right? And this is now, let's say, driving further design approaches of the HDFS system towards the so-called replication strategies. And these are, of course, configurable. So there you find different ways how it is handled. There's some default values, always keeping 3 replicas, for instance. But in the end, it's, of course, up to the administrators of the systems that you have there, not for the user. Usually the user doesn't see anything about this, but you can immediately think about if it's about replicas, when you know a little bit about costs of data, of course, storing them for a long time, maybe replicas cost also. It's something where you have to think about that, let's say, doing always 10 replicas of every file would be perfect from the throughput for computing. I think you can be very sure if you keep 10 times all your files that there will be no hardware error always at the same time, that you cannot work and access the data. But you can immediately see 10 times the data, there you go in the cloud, and also pay the price for it, right? It's a cost that you have to pay. So essentially saying that there needs to be a smart balance strategy. How much is, let's say, replicas created for very much data which is very important to the company, maybe there you have higher replica numbers. Others which are often computed, for instance, there are more replicas. So of course this is a bit adjustable and really depends a little bit on your application domain problem. But the good news is this is inherent in the framework. So nobody is now doing manually and says, I have my nice distributed file system here in the form of Hadoop. It's a specialized file system. It is doing all that for you. So you don't have to think about the replicas to put the data 3 times manually, let's say with SCP or copy on different servers now. This is what is done directly when you inject it. And we will see this in the practical lecture 5.1. When you inject this into the HDFS space, then this replication strategy will automatically kickstart and will already, as we see here on the right-hand side, shard the data, so to speak, or split the data is another word for it. So it will have, as you see, firstly, the splitting. So there are different parts of the data, let's say 1, 2, 3, 4. And when this is done, this sharding or this tiles will be distributed after this replication strategy that you defined. Here we see 3 replicas of this particular block of the data. And now if you take these different blocks of the data, you see them and put them together with different varieties of this different other blocks you see in the first 1, 3, 4, and another 1, 2, 3, and so forth. You will see then this is of course adding to the reliability. If now one data node goes off, let's say the third from the top, right? It's not anymore active. I still can come to my data in one way or another on another data node. And of course, again, it depends, of course, how many errors come. It depends of how many replicas you have, but this strategy really stands the test of time. And the good news is, of course, think about it's not visible to the end user. It's just the administrator that, of course, then goes into this and thinks, oh my God, why is the data node down? So we have to get it up again in case another data node will fail and another maybe. But usually that's unlikely. Hardware errors come and software errors come, but not in this, let's say, exponential crash. Or it's really a very serious bug or a very serious element. But these are nowadays coming more with software updates from vendors, which already warn people. So there are maintenance windows, so to speak, on these large systems, where part of it is then really closed for some time to really test also the new updates on the software, so that not end users are really experience, let's say, a large downfall on the system. Nevertheless, let's clarify some aspects of the HDFS architecture we have already explored. So we have seen the different roles, which is very important. So the roles could be also exam questions here. So again, your attention. Master and head is the manager, as we discussed. So there must be someone that has so-called file metadata. It is so-called in the Hadoop space a name node, although some people call it master node, head node, name node, secondary name node. So all of them mean a little bit the same thing, that basically those are very specific nodes. There are not many of them, usually one. If you have, let's say, very strong installations, you would have maybe 1, 2, or even 3 of these master and heads. As I said, a name node and a secondary name node, just to be sure that if the primary name node goes down, we have another one that knows where all the files are. So in a way, attacking here the single point of error, right? But this is an important strategy. Of course, this is not where the scalability really is. It supports the scalability, but in the way that it controls more and more workers doing the real job. So the master and head keeps, let's say, computationally, relatively with a very, very small footprint. It just keeps track of all the data. Of course, this requires some entries on which workers are which data nodes and what types of files or blocks, to be honest, really, that's what they talk about, and chunks of those files are really essentially on these data nodes. So all of this management, so to speak, and keeping this track is done in this single entity, while the workers now, they actually have almost no idea that they exist in a sense. They just contribute to the big picture. and they have no idea about basically the replication strategy in itself of saying, I am the one for 1, 3, 4. They're just storing the data. It's about the whole engine to know that actually we have, let's say, just 2 replicas of 3 or block 3. We have to create another replica, and then it's done. And it is, of course, then a task given to these workers to do the transfer on behalf of the users, which will never ever see this. So it's automatically done. But while talking about this, of course, technically, you can see that there are lots of questions, right? Replicas require then transfer again. And this could take time in big data times when you have large capacity. Of course, take away the message that usually you break it down in several megabytes, or let's say 64 chunks, right? And then, of course, the transfer gets, especially by the interconnect we have in these days today, very quicker. But still, if it is, let's say, petabytes of files, it's something behind the scene done, right? So it's not something very quickly. But the good news is it's really managed automatically. That's what we want. As we said, if we scale to many, many workers, as installation with 60 or 70 Sparks worker nodes, then we don't want to do this all manually. And it's automatically done in this framework. So this is about the name nodes, the data nodes, and the so-called file name or file system namespace, if you want. It is also an IROTS, an inode from Unix on steroids, if you want, a little bit a higher entity, not directly in the file system, but in this Java space file system on top of the normal file system. Of course, in a way, it has to interact with a real file system, right? And that is more than having this kind of blocks rather than real files. And this is where then also the replication strategy comes. It can do really huge amounts of data. This is, of course, the advantage of Spark, of Hadoop, especially for those data which are accumulated over times to be big and never be really transferred. So when we see that now, and parts of it already covered, right? It's basically the kind of head node, which is very important here, the name node that we already observed also in the setup of the MS Azure cluster. You have seen that when we had the script that we used in MS Azure, we already had this kind of interesting different settings in one of the previous lectures, that even Spark has a head node and then several, let's say, worker nodes. And the same way we used already without knowing basically this concept of then what I also showed in the practical lecture 3.1, really in the demo. When you look on the YouTube, you see that really it gets to different tasks. We see the to-dos of the task, the status, by using the Jupyter notebook. And then basically we see that it's all parallel executed on different tasks following these ideas. And of course, this is an interesting framework now, which you can do lots of things, and which brings us to an interesting setup that the scalability really relies on the number of worker nodes. And with this, theoretically, you could scale more and more, but it also says that we can reduce, right? Not in the form of map reduce, rather on reduce again on the number of workers when we don't need them. Of course, then maybe your availability goes down because your data nodes get significantly shrinked, but you can do up and down essentially with the worker nodes, and then doing this automatically will also meaning that the replication strategy will follow suit. And all of this is done without the administrator to necessarily copy all of this. Of course, there's still work to be done in a real installation. Of course, for administrators to think about how many replicas, how many name nodes. As I said, a secondary name node maybe makes sense, but this is something where it's much more easier than doing it all manually. And this is a summary, so to speak. If you have all the data nodes, again, think about you would have parts of the data. That's how you see it. If you want to look at, for instance, in the Hadoop space, we look on this in the practical lecture 5.1, of course, that the data you see is now on the file system rather like this, part 0, part 1, right? And of course, think about that. This is now kind of shredded into different replicas, and then of course having each of the individual blocks totally distributed on all the data nodes. And this is basically what you see a little bit there with indications that there's a 1.3 is basically in this part, and then from a complete different replica you have maybe from a different part of the data 3 replicas that you put on different, let's say, nodes and blocks, right? So, and with this you have a mapping strategy on the top from this replication policy or the view on it to the real situation, right? You see it's completely distributed. You said you want to have 3 replicas of, you know, the blocks 4, 5, and 2, 4, and 5. And you see basically it's completely separated on different data nodes. It of course would make sense now to put on one data node all the 2s or all the 1s, right? So that would of course destroy the idea of the replicas of saying that the data node may go down and then takes everything with it. So in a way, I think it's not so tough to understand. In the end, it's about replication and automation. And let me just come again to the example of Facebook back to give you some motivation that the thing that we do here in the course is really used with big data on a daily basis. Here we see on Facebook. Of course, not for everything in Facebook. We will come to lecture 11 to graph databases where they have also interesting aspects like things like liking and so on. But here it's used for a very specific purpose on the search index, complementary to the HBase and also to the MapReduce. That basically then nothing else than building the index in parallel over many, many worker threads. So Facebook has also interesting engineering pages. So if you're actually interested in how they work, they have interesting pages to go through. Just give you one message, of course, in some of the discussions, it is a company and we discuss, of course, with them. Sometimes we don't get really the cutting edge source code, right? MapReduce was one example, came later out. In some discussions, it was also revealed with them in some of the areas where they use MapReduce, they don't use it anymore, meaning more graph databases and so on. So of course, it's a company, so you will never really know what they do, right? So still it gives you a light how you operate and actually can deal with big data because Facebook is doing with us research, right? There are not many companies in the world that have that much data than Facebook, Google, and perhaps a couple of others that we don't really know of, or governmental organizations. So this is also a very good takeaway message that we can also learn in research how that is done. And they have, of course, also the financial mean to do so and have also very good researchers. Now, let's say another aspect of this is just to conclude on the benefits of the file replication. Of course, we know also from the different ideas that we have, we see redundant, inexpensive areas of this, RAID systems, that basically replication is always good. Copying your data to be sure is always good. We do that as humans when we have a very good, soundtrack and we don't want to lose it. We maybe have it twice as MP3 somewhere. So this is important, but it needs to be easy to manage. We don't want to do this, right? So that is what we can do here. And this is really fault tolerant. So it is reliable, dependable through this data replication strategy. That's nice. And with this has really shown to be a very good model in practice. So just think about speed a little bit, but because people were saying, okay, Apache Hadoop is so terribly slow, I'm not using it. And you see here, Apache Spark is using more memory. And just coming back to this, what we already had in one of our previous lecture, in lecture 3, here you have, of course, now the downfall a bit of it. When you write to HDFS and read and read and write, and again, what machine learning is doing, then HDFS has some drawbacks. It's not just reading data, like lots of text to do word count, it's also writing data back. This immediately gets a little bit problematic, right? And for machine learning, we have to do this every now and then, having an iterative approach. So we will have lots of interesting examples in this area. I will show much more in lecture 5.1 and then also go to this fact back that we have an iterative approach in machine learning. So it's not perfectly the best model maybe for doing MapReduce. Still, of course, it enables a lot, as we see here also with Elastic MapReduce. This is in the Amazon Web Services. We will talk about it, and also your assignment is related to it. So it would be good to be at the next practical lecture 5.1. There I will also talk a little bit about more the larger ecosystem. You already have seen Hive indirectly with SQL. structured query language for databases, but there's also lots of different aspects. Mahout is a complete machine learning framework on top of MapReduce, basically, and you have seen HBase used by Facebook for NewSQL. NoSQL always stands for key value pairs, and we will talk about it. And when you go to the right-hand side, you see really it's implemented. It's not only used by Facebook. You see these are really offered as daily tools in the Google Cloud as data proc service, in MS Azure as HD Insight, and we will see also in Amazon it has its equivalent. So in large, what I want to say, it's really used in practice. If you want to create it your own, we will talk about it. Maybe in your company, if you have a startup, you want to start small before you go basically to Google and Amazon and pay, use OpenStack. It has some benefits of having a node managers and name nodes that you already have, a very nice mapping of the services and structure component in OpenStack. So in a way, it's very easy to do this, and in a semi-automated fashion, and we will talk about this in lecture 13. Now, coming back finally before we close the lecture of today, finally I want to give away the message before we go really in depth to it in the different lectures, 11 and 12, they are all related to this. Scalability is a big issue. I talked about it handling errors, but what about managing all of this as an administrator of data centers? So this is a semi-automatic configuration deployment we need. There are two tools we will talk in depth about it, which is Docker. It's really container technology. You see this where it's basically including already applications bundled together on Docker to be, very easy deployed. And you see on the right-hand side, you can find already Docker images for this, for a data node, for a slave, for a name node, and so forth in the Docker Hub repository. And of course, here you see then, once you have this, the question is how you go back big, right? Across all the nodes. And you can do with Kubernetes, a very nice tool, actually, a very good idea of getting your cluster quickly automated, configured, and with these container orchestration strategies. We will talk all of this. I just want to give you the point that this is, of course, directly related to the number of workers in MapReduce. And that's why it's a key issue. It's related to the number of data nodes that you have. Of course, that's why we have to talk about it, but we cannot cover everything in this lecture here today. With this, I really have my final slide. Think about that, of course, it has limits. We discussed some of them, which was the weather prediction of this lonely sailor here. Even if he swims in big data, the waves are propagating through all his basically area that he sees. So there, having a complete independent parallel approach would be probably not good. Standing for all the physical simulations that you have in CFD, computational fluid dynamics, which would be this case, but also in weather prediction. Usually you will find that is not driven by MapReduce. This is driven by high performance computing, message passing interfaces, shared memory, and distributed memory programming paradigms. Much more we cover actually in the HPC course. It is also parallel, but it's not as parallel basically as we do it here. We see more and more, of course, that the buying patterns are changing. So you also have to think about that certain analytics maybe don't change and don't make sense anymore to put on old data. So you have to have more strategies of keeping old separate from the new data. With this, all the big data ideas is, and the replicas is not anymore there. You have different replicas. So that's again to the complexity. That's what I'm saying. And if you have lots of user actions that we see more and more coming, so you can comment on items, you can rate items, you can like items, you can suggest them to others, you can share them. All of this interaction must be put in the database, and hence we have a problem because we write all the time. These databases with HDFS and basically the MapReduce approach was much more oriented to reading. Yeah, reading, analyzing data, that's what we want. We don't want to go back and always writing. If you do this with this file system, it's not really optimized for this, especially in a large parallel way. Then you're again in the HPC world with parallel computing. You write simultaneously to one file in parallel computing with parallel file systems. So you see lots of these things have to be considered all the time. And this, another example is also the machine learning. As we said, there's an iterative MapReduce more or less needed. You just not go once through the data, you go several times through the data. So people have worked on this. Geoffrey Fox is a very prominent name, for instance, who had some tools in this area. There's Hadoop, and there's also iterative MapReduce from Geoffrey Fox's team itself. But of course, this means that MapReduce alone is not sufficient. Maybe we need to do more. You can do simple things, but when you have, let's say, a very complex machine learning algorithm like the support vector machines, then it's of course already a bit challenging to really work with this paradigm. And that's really what I wanted to leave on the table here for you. This video is a very nice summary, and take away the message that we have much more practical example in our practical lecture 5.1. And yeah, thank you very much for attending today, and see you on Tuesday.